Hello, everyone. Welcome to today's Quantum Spacetime seminar. We are very happy to have Katsuki Aoki from YITP and Kyoto University, who will tell us about gravitational positivity bonds. Over to you, Katsuki.
Okay, thank you very much. And thank you for giving me this opportunity. So I'm Katsuki from YITP. So today I'd like to talk about some consistency condition on the gravitational EFT based on a couple of our these papers. So let me start. And if you have any question, please feel free to ask me anytime. So yes, in this talk, I'd like to talk about EFT. And the underlying idea of EFT is IR physics must be insensitive to UV physics. So if we know the fundamental theory, of course, by definition, it's explain everything from the high energy physics to the low energy physics. But in many situations, it's practically useful. We have to think of the EFT. Because, for example, even if you know the fundamental theory, like QCD, it's really difficult to extract the low energy information from the UV physics. So QCD is strongly coupled, so at low energy, it's almost impossible or very hard to find the low energy predictions. Or in the gravitational theory, the situation is a bit worse because we don't know the UV theory. We don't know the quantum gravity. So we know the GR, but we don't know what is the underlying fundamental theory. But the good point is IR physics is insensitive. That's why we can consider the low energy theory directly, and we can find the low energy predictions based on the EFT. But the point is, I said that the IR physics must be insensitive, but the two are not totally independent. And this is actually the point. And recent years, many groups try to find a consistency relation between the IR physics and the UV physics. And IR physics here means that what we can observe. So in that sense, the standard model and general relativity are definitely the correct theory in the IR physics. And also that we may consider the, say, beyond the standard model. In some sense, this is a UV physics, but in this criteria, beyond the standard model is still IR physics because we can test it. On the other hand, UV physics means what we want to know finally, so like a quantum gravity. But you know, the expected energy scale of a quantum gravity is very high, so it's almost impossible to directly detect the quantum gravity. And if two are totally independent, then we cannot say anything about UV physics. But if we have some relations between the IR physics and the UV physics, then we can use it. So we can use these consistency relations to, for example, make predictions on IR physics. So this is like a top-down direction. So assuming some using this consistency relation from the UV physics, we may get some prediction on the IR sector. Or we know the IR physics well, like a standard model, GR, and so on. And then using these relations, we may get some information about UV physics. So this is like a bottom-up direction.
Sorry,
so
can I? Yes. Please excuse me for interrupting so early. But can I ask you one thing?
Yes.
You know, one of the lessons from ADS CFT, it seems to me, is that what is IR in the bulk is UV in the boundary theory. You know, and so the notion of IR or UV themselves are not duality invariant. And it's a bit too early, but there's something similar in de Sitter space as well. So when you refer to IR and UV here, which description are you using, if I may ask?
Sense, this ADS CFT gives some relation between IR and the UV physics. So here the classification is that whether we can observe or not. Just it. If we can observe it, this is IR. And if we cannot directly observe it, then this is UV.
Okay.
So this is a classification here.
Okay. Thank you.
Yeah, welcome. And yes, ADS-CFT would be one possibility to find some relations. And in general, this kind of program is called swampland, especially in the context of string. But I think before going to details, I should say that there will be no definite criteria, simply because we don't know UV. So actual problem is what is a self-consistency condition from the assumed UV physics. So we may have some expectations, or may have some plausible assumptions like unitarity, or maybe string could be expectation on UV. And then under this assumption, we can get some consistency conditions on IR physics. So this is our actual problem. So in that sense, it's really important to understand what are the assumptions of these consistency relations. And also in this context, scattering amplitude do a really nice job, because the general assumptions are already enough to find very strong constraint. So here, the general assumption means that essentially these four assumptions, and I will explain what the meaning and consequences. But before going into the detail, I think we can easily understand find a textbook example. So if we assume the unitarity or partially wave unitarity, then we can find that the amplitude is essentially bounded by 1. So this means that if we find some violation of this partial wave unitarity, this means that the theory is in some sense inconsistent, or we need new physics to recover this partial wave unitarity. And actually, this program was used to find the Higgs boson. So before discovery of Higgs boson, we know that the theory of weak boson violates the partial wave unitarity, and then the Higgs boson is needed below the TeV scale, and indeed we found it. So this is one textbook example, but recent years, we combine these four properties, especially analyticity and boundedness, and then we get a stronger constraint, and this is called positivity bound, and this is a topic.
So one clarification.
Yes.
This ms comma theta is less than 1 in modulus, you say, but should it not be for a particular spin rather than particular theta?
Yes, it's a finite theta, if I remember correctly. So amplitude is generally can be extended into the complex complex plane, but this should satisfy in the physical region. So unphysical region, this may be violated.
No, but I thought you would want to fix the spin rather than the theta.
Sorry, S?
No, so S is there, but I'm talking about theta.
Theta is an angle, yeah. And angle must be finite. So it's not complex. Just a real number.
Sorry, the partial wave unitarity condition that I'm aware of would be that you do not work with a fixed theta, but rather work with a fixed spin.
This is fixed theta.
Yeah, so I'm not okay. I'm not familiar with this kind of bound for fixed theta.
Actually, the originally partial wave unitarity states that the coefficient of the partial wave expansion must be less than 1.
So those have labeled by J, right, rather than theta.
Yes, yes.
So you need to fix J.
Sorry, this is just like a naive discussion.
Okay.
The precise statement is the coefficient must be less than 1.
Okay, thank you.
Yeah, sorry. Because this is not so important. That's why I just put the rough expression. So anyways, first I'll explain or I'll review the general properties of amplitude. And after explaining it, I discuss how to find a positivity bound, especially in the context of gravity. And then I will discuss the implication, phenomenological implication of this gravitational positivity. So let's start with the textbook explanation about the scattering amplitude. So first, probably the most important assumption is the Poincare invariance here. So Poincare contains the translation part and the Lorentz part. And assuming the translation invariance, we can conclude that there exists a conserved current, and using this four momenta, we can label the asymptotic state. And using this P, we may prepare the initial state and final state, and we may consider the probability of this process. And this S is called S matrix, but it may contain the trivial part, and I mean the P1 just goes to P3, and P2 just goes to P4. So this trivial part is not interesting. So usually we discuss this interacting part, and this interacting part gives the amplitude. So this is a definition of the amplitude after subtracting the conservation. And originally the amplitude is a function of the momenta, but using the Lorentz invariance, we can say that the amplitude must be a Lorentz scalar. And using the on-shell conditions, then we find that the amplitude must be a function of the two of the Mandelstam variables, usually S and T. So we will consider this function, this is just a complex function, MST. And the second assumption is the unitarity. This is also the textbook explanation. But anyway, So this unitarity states that the probability is conserved. So SS star is 1. And using this equation, we find this expression for R. And one important consequence is in optical theorem. So setting t goes to 0, and this is related to the imaginary part of the scattering amplitude. Then in the forward limit, the right-hand side becomes a square. So this means that this is positive definite. So the unitarity says that the amplitude in this regime is strictly positive. So this is one consequence of the unitarity. And second important consequence is the existence of singularities. So let's consider this energy regime. So S is less than 2m squared. So S is roughly the energy square. And in that case, let's consider this equation. And the right-hand side is non-vanishing when the n is on shell. But if the S is less than this quantity, then only the possible on-shell state is a one particle state. So this means that the imaginary part is non-vanishing only when the S is exactly the same as m squared. This means that implies that the imaginary part m has something like a delta function here as the m squared. And if we increase the energy, then the 2-particle state or 3-particle state are possible. This means that the imaginary part is continuously non-vanishing, and it's positive due to the optical theorem. But anyway, they are non-vanishing beyond this reading threshold. And this is the behavior of the imaginary part of the amplitude. And this implies that this kind of analytic structure. So I mean that the amplitude in the complex S-plane must have a pole as the m squared, and they have a branch cut beyond the reading threshold. Of course, using the Feynman diagram, we can easily understand these singular properties. For example, if you consider the propagator has a pole. So this is just pole. And if you have a loop integral, it may give the square root, and it may give a branch cut. But the important point is that these singularities are inferred from the unitarity alone. And then I talk about the so-called analyticity. So I explained that we have expected singularities from the S channels, and also in the relativistic amplitude, we have a crossing. So we also have a U channel. So we have a U channel singularities here. And here I consider the amplitude for a fixed T. So meaning that we don't have any T channel singularities because T is fixed away from the singularity. So only the S and U channel singularities appear in the complex S-plane. And the assumption is there is no other singularities. So we have a singularity from unitarity, but we don't have others. And this is called analyticity. And this property is crucially related to the causality, because causality may be used to extend the regular region here. So on the real axis, we have a regular part. And this regular region may be extended to the upper half plane of the complex S-plane or lower half part. Then we may conclude that there is no other singularities by using causality.
Sorry, when you say no other singularities, you mean no other singularities on the principal sheet?
Right, exactly. Only on the first Riemann sheet.
Thank you.
Yes, thank you.
So I'm sorry not being an expert. If there had been any other singularities, it would have violated causality. Is that right?
I think so, yes. At least in the case of gapped system, I think it's almost proved.
Okay.
By using causality. But the actually important thing is that in the case of massless particles, M is 0. So we don't have any regular region here. So in that case, it's would be subtle, but it's almost accepted that even in the massless particles, we have a same analytic structure.
I see.
But I think it's not rigorous.
Okay. Thank you.
Yeah, thank you. Yeah, actually, as I said, in the presence of the massless particles, there is no regular region on the real axis. But luckily, we know that these particles are weakly coupled. So photon is weakly coupled, and graviton would be weakly coupled, at least below the Planck scale. So this means that we can use a perturbation theory. And at the reading order, we just have poles. So this doesn't change anything. At the loop level, we have some problem, but at least using perturbation theory, we can understand the analytic structure, even in the presence of massless particles.
Okay, thank you.
Yes, thank you. Thank you for the question. Yes, this is the third assumption on the analyticity. And the last assumption is boundedness. So this means that the asymptotic behavior of the amplitude. And in this context, one very famous and important result is called Floyd-out bound. And this is again the gapless system, but in the gapless system, all the mentioned property plus locality. Locality here means that the number of derivatives is finite. And this assumption implies that this behavior. So amplitude is bounded by S squared in the high energy limit. And this determines the asymptotic behavior of the amplitude, but again, this is applicable only for the gapless system. Actually, boundedness in gravity is quite subtle because we have a S squared. So this is a graviton T-channel exchanges. So we have a graviton, and the graviton is universally coupled, so it must give us this kind of behavior. So 1 over T means that the graviton is massless. So T equals 0 is a pole, so graviton. And we have a S squared, and this 2 is related to the spin. So graviton is spin 2, that's why we have 2 here. But this means that actually this GR amplitude is a boundary of the disk Floyd-out bound. So GR amplitude grows as a S squared. But we know that at least in the case of part of the string, we know how to GR amplitude is modified. So GR itself is not UV complete, so we need some UV completion. And in the case of string, actually amplitude is modified like this. And this is called Lecce behavior. And physically, this behavior implies the existence of a family of particles. So in the case of string, we have a string, and the string, we have a string higher excitations, so corresponding to the higher spin state. So we have a family of the particles, and this family of the particle gives or modifies the power. I don't explain any details, but actually the spin, in the case of string, we have this kind of behavior, and similar behavior can be found in the QCD, because QCD also predicts the higher spin state as mesons. Then we have a similar behavior.
I have a question.
Yes.
What is the origin of the M Planck square term in the denominator?
Because this is gravity. Because gravity coupling constant of gravity is Planck inverse.
Does it originate from the Newton's constant or something?
Yes, that's it.
Okay.
Just G. Yes. And anyway, the point is we have a small modification in the power, and alpha prime is, for instance, string tension. So this is a positive quantity. So this means that if the T is slightly negative, then the power is slightly less than 2. Then this stringy amplitude satisfies a similar bound, so S square bound. So we assume that this property. So we assume that, of course, GR is not UV complete, but we expect the GR is UV completed. And this UV completion provides this kind of behavior. So even in the presence of gravity, we assume that the amplitude is bounded by S squared. So this is our fourth assumption, and in the negative T region.
But what about the T positive region?
In that case, I think we don't have this bound. Because if, for example, if this is correct, then the positive T means that the power is greater than 2.
Yeah, so it wouldn't hold in that case, right?
Right.
Whatever you're saying.
But we only consider negative T region. So we don't talk about any positive T region.
You know, physical scattering happens at negative T.
Yes, that's true.
Okay.
Yeah. So anyways, our assumption is that amplitude is bounded by S squared in the negative T region. Yeah, this is also an important point. Then let's do a complex analysis. And using this complex analysis, we can derive the so-called dispersion relation. So this is just elementary complex analysis. We consider the Cauchy's integral formula. So this states that the amplitude or some complex function, or the derivative of the complex function, is written in terms of integral of the complex function itself. And here we assume that the n is same or greater than 2, and t is negative and fixed. And since this is complex integral, so we can deform the contour as long as it doesn't touch the singularities. Then we can deform this contour to like this. So integral along the branch cut, pole, branch cut, and the infinity. And thanks to the asymptotic behavior, we can ignore the contribution from the infinity because n is same or greater than 2. Then we find this equation. So this is called dispersion relation, and this states that essentially the Sn part of the amplitude are determined by singularity. So this is the original Cauchy's integral formula, and we deform the contour and integral along the branch curve, U channel, and poles. And physically, this says that this part related to the SU channel exchanges rather than contact diagram. Because as I said, the singularities are essentially related to the internal onshore state. So these are exchange diagrams. And of course, you can easily understand. So if we consider this diagram, we have a propagator. So if you do a Taylor expansion, we find a non-infinite number of the Sn part. So this is a non-polynomial because we have an inverse. And the same is true for the loop diagram. So calculation is more complicated, but we have some loop integral, and this is essentially the non-polynomial function. So if you do a Taylor expansion, we have an infinite number of the Sn. On the other hand, if you consider contact diagram, then this is a kind of local interaction. So as long as the number of the derivative is finite, this gives just some finite polynomial. And our old assumption implies that this diagram should lead to the n is less than 2, and the higher n part are originated from these exchange diagrams. So this is a physical meaning of this dispersion relation. So these are the review of the general properties of the amplitude, and then I will explain the positivity one.
Sorry, could you go back to the previous slide? I didn't understand why contact diagrams could not contribute to Sn for n greater than 2.
Actually, this is a consequence from the probability locality or boundedness. Because this says that this quantity has to be related to the singularities, not the regular part.
So if we did an alpha prime expansion of the effective action of string theory, there would be terms which would contribute at all orders.
Okay, in that sense, this is based on, in some sense, UV complete theory, not the EFT. This is a statement on the UV theory. But of course, in the EFT, we have a contact interactions, like a higher derivative interactions. And this leads to the higher order part. And this is a topic in the next section.
Okay. Okay, thank you.
Yes, thank you. Actually, this is a really important thing. So this is a dispersion relation. And this is a kind of identity. So if we know the full form of the amplitude, this has no information. But the point is that in the right-hand side, we need a UV information because we have an integral from the IR to infinity. But in the left-hand side, we have some amplitude evaluated at some point, at some finite point. So this means that we can compute the left-hand side based on EFT. So after here, I don't say anything about EFT, but now I introduce a notion of EFT. And I use the EFT to compute the left-hand side here. So now M in the left-hand side is EFT amplitude. And in the EFT amplitude, we have a higher derivative collections because we need to integrate out the UV degrees freedom. And this gives, for example, this kind of interaction in the case of scalar as a leading order. So this
now
is the one thing.
It is less than lambda square and not less than 0.
Sorry, here. Maybe this is the absolute value, sorry. Because the EFT is buried below some energy scale.
No, but is T not less than 0?
T is, sorry, this is absolute value and T is negative, yes. Negative, and its modulus is less than lambda square, sorry. Because the EFT is a kind of low energy approximation, so it's valid only at the low energy regime. So these values or modulus of these values must be less than cutoff. But yes, sorry, T is negative. Okay, so this is one example EFT, the simplest one, scalar EFT, and we have a kinetic term, and if it's massive, we have a mass term and some interaction, and we have a derivative interaction. And in that case, actually, this gives just a S0. This is renormalizable. This gives a S0, but this EFT correction gives a S square. So that implies that the left-hand side is essentially a function or just a coupling constant on EFT. So this is a coupling constant. And this coupling constant of EFT is related to the UV integral. So this is the meaning of this disperse relation from the EFT perspective. And what we want to do is find some constraint on the right-hand side. And this is equality. So if we find some constraint on right-hand side, this directly gives a constraint on the left-hand side. And this is a constraint on coupling constant of EFT. So this is a basic idea. So yes, the point is we have a
Katsuki, one question,
yes.
somewhat technical. So the left-hand side here, which is the nth derivative, appeared because you did the dispersion relation with s prime minus s to the power n plus 1 in the denominator, right?
Right.
Now, there are some papers where they do the dispersion relation, not like this, but they introduce these not as an nth pole, right? Not as an n plus 1 pole, but rather product of simple poles at various locations, right? So that they preserve the crossing symmetry. I'm talking about the work by Leonardo and collaborators, Leonardo Rossi and collaborators. So is there any particular advantage of doing it this way versus that way? You see what I mean?
I'm not so sure of this paper. Maybe I missed, but anyway, I think that there is no difference. So because without derivative, we can derive the dispersion relation directly. In that case, what's new is that we have an undetermined function of t plus this integral.
Okay.
And we have a s times some undetermined function or just a constant times undetermined function of t. So since these are undetermined, we have no constraint on the leading zeroth order in S and first order in S. So in any case, we need to take a derivative.
Okay, thank you.
Yeah, thank you.
Isn't there a relationship between the Taylor coefficient and the contour integral with respect to the higher order poles? So what is the relationship here?
Sorry, what's the question?
The question is, isn't there a relationship between the higher Taylor coefficients and an expansion in terms of contour integrals in terms of higher order poles? So this looks very similar to that.
Yes, exactly. This is just it. Because in some sense, this coefficient or coupling constant of EFT is just Taylor coefficient. Right? Because if you integrate out the UV mode, we have say phi square times propagator phi square. And if you do a Taylor expansion, this leads to this part. So it's same.
I'm talking about the relationship that you have on the first line.
You mean
it's not exactly. It's no.
Yeah, the same because this is now UV mode, and integrating out UV mode means that we do in some sense Taylor expands this propagator.
Okay.
Then we get this kind of effective interaction after Taylor expansion.
No, I'm talking about the D and DS and MS T's and zero that relationship.
Sorry, which one?
the first, go to the next page, next slide.
Next page.
Yeah, the relationship on the first slide.
Relation to first slide.
This relationship. Yeah. So this relationship has
this relation between this and right?
No. The left hand side and the right hand side. I mean, isn't there a similar relationship in terms of Taylor coefficients in an expansion of a series and its
you mean the Taylor expansion of this one?
Yeah. So if you have a contour integral with a pole with a n plus 1 of the
I
pole,
see.
then that's essentially the derivative of the residue of that is just the derivative of the m. But
sorry, Somnath, are you talking about Cauchy's theorem?
Yeah, Cauchy's theorem, exactly.
Yeah, I think he's aware of that. Yes.
So
this is just identity.
Relationship between Cauchy's theorem and this?
Yes,
that's it. Yes.
Yeah,
But
please,
here
Katsuki, go ahead.
you have just 4m square and to infinity and not the entire thing. So I'm just asking whether what is the exact relationship?
There is some non-analyticity in 4m square to infinity, right? So he has to undo the contour and wrap it on that cut 4m square to infinity, and that's how he gets this relation. On the previous picture, previous page is a picture of that contour deformation.
Yes, yes.
Sorry, and if you're asking Shobdatta how he gets the left-hand side, as you say, you Taylor expand the numerator until you get a simple pole, and the coefficient of that is the left-hand side. I think that's what you're saying, right? And I think that's correct.
Yes.
That's correct.
Yeah, that's correct. So if we know the UV theory, we know everything, and this is just in something Taylor expansion. So our actual problem is that we don't know the UV, but we know only EFT and how to get the constraint on EFT. So okay, let's proceed. So yes, positivity 1 arises from the UV constraint. So we know that this mathematical equality, and we can evaluate the left-hand side by using EFT. So what we want to find is a constraint on right-hand side. And this is just this is not essential, but it's useful to introduce a so-called pole subtracted amplitude. So this M tilde is defined by the M minus poles. And these poles are poles associated with low energy degrees freedom. So we can still compute this M tilde by using EFT. And why this is useful? Because now the T-channel pole is manifest. So originally this amplitude contains poles, T, S, T, U poles. And we also have the poles in the right-hand side as well. And this S and U poles are canceled. So what we have is T poles after using this T-channel pole subtracted amplitude. And why this is useful? Because we know the property of the T-pole. So T-pole is essentially given like this. So M is a mass of the extended particle, and J is a spin of this particle. So this arises from the low energy degrees freedom. This means that we know that the existence of a spin 0 particle, spin 1 particle, spin 2 particle, but we don't have any higher spin state. And we are taking derivatives. So if J is less than N, then this pole doesn't contribute to the dispersion relation. So this means that if we have a Higgs boson, so spin 0 particle, and this may give a T pole, but this doesn't contribute to the dispersion relation. But in the case of graviton, this is different because when N is 2, graviton is spin 2, then this graviton pole contributes to the N equals 2. So this explains that the positivity in the presence of gravity and without gravity are completely different. If we ignore gravity, then we can completely ignore this T pole because we are taking the derivative. But in the case of gravitational amplitude, we must take into account this T pole contribution. So let's first discuss the positivity bound without gravity. So in that case, as I explained, we can simply discuss the T pole. So this is a dispersion relation after using the SE crossing. So it's relatively simple expression. And actually, you can easily see that this is positive quantity because this is the amplitude, imaginary part of the amplitude, and we may take a forward limit. And in the forward limit, this is integrand itself is a positive definite. So this means that this integral is, of course, positive quantity. So this concludes that the right-hand side is strictly positive. So we don't know any information. We don't need any information about the UV theory. We only need the unitarity of the UV theory. Then this unitarity concludes that this right-hand side is positive and right-hand side is left-hand side, so trivial. Then we find this inequality, and this is called positivity bound. So EFT amplitude, roughly speaking, EFT amplitude has to be positive to satisfy all the mentioned assumptions. For example, if you consider this scalar EFT, then the statement of positivity is C1 has to be positive. So this means that if the EFT predicts a negative sign, this is in some sense consistent or inconsistent with at least one of the assumptions, like unitarity or causality or locality. So this is a statement of the positivity. And actually, we can also improve the positivity. This is called improved positivity. So yes.
Katsuki, one question. Why is it that you choose to compute the dispersion relation at S equal to m square minus t by 2?
Because it's simple. I mean, we want to use the SU crossing, and this is a crossing point. So originally, S channel and U channel gives a different contribution. But if we evaluate this point, the two are the same.
Okay. The contribution of the cut combines.
Yes, right.
I see. And then for the positivity bound, you have evaluating the left hand side also at t equal to 0.
Yes.
But there is a more general statement, right? Okay. No. Sorry. Yeah. Okay. So you on the right hand side you only have t equal to 0 thing to be positive, so that's why you want to set t equal to 0. Okay. Thank you.
Yes. Thank you.
I have a question.
Yes.
If the thing really is equivalent to a Taylor expansion and corresponds to a contour integral around poles, which is then expanded to include the branch cuts and other poles, then where are the other poles?
The other poles?
You in that previous picture that you showed, you had some other poles and other branch cuts as well, right?
In here?
No. Can you go back to the slide where you showed the?
Maybe this one?
Yeah, this one. Yeah. So if it's really a contour integral initially around that S point, and then finally a contour integral around the branch cuts, then where are the other branch cuts? Where are the contributions of the other branch cuts and poles?
Yes. Originally, we have 4 contributions: S channel, U channel, and SU poles here. Here. And I introduced the pole subtracted ones. So poles are subtracted for both sides. Then the SU poles disappear here. But still, we have 2 contributions, S channel and U channel. And they are combined by evaluating at this point because of the crossing symmetry.
I see.
Oh, just one question, clarification that
sure.
You calculated these coefficients at S is equal to 2m square minus t by 2 and then t is equal to 0. I mean, this is just S is equal to 2m square, right?
This is just to use these properties because I want to use crossing symmetry. Then I just evaluate this point, and also I want to use optical theorem. That's why t is 0.
No, I'm just asking. As it is written, it can have different. I'm just saying that let's say you have S square plus t square. Okay. Let's say the derivative is just S square plus t square, and what your answer will be? It is just 4m to the power 4. That's all, right?
Yes.
Okay.
So this quantity is just C1 over M4. Then this must be positive. Then C1 must be positive.
And also one thing that if your amplitude or derivative of the amplitude, nth derivative is proportional to t somehow, then you can't bound that coefficient. Is it?
Yeah, this is original equality. So we can leave all the bound from this inequality.
Okay. Thank you.
Sorry, Katsuki, just to press on that question. There is no parameter in this inequality that you are getting, right? So if you had higher derivatives, even higher derivative terms in that ... then the inequality will not be purely on C1, right? It would be on some combination of all the coefficients.
Right. Because if we have more higher derivative interactions, this may contribute to the n equal 4, for instance. Then we get some other constraint.
Oh, I see. But you can isolate the ones that you want.
Yeah, because this is just parameterization.
Okay. There is an n as a parameter. Okay, thank you.
Yeah. Okay. So the next topic is a so-called improved bound. So this is again the dispersion relation, and the idea is quite simple. So I use the optical theorem, but actually we can compute the sum of the right-hand side because the integral runs from the IR to infinity. So we can still compute the IR part because the EFT should be valid below the sum cutoff. So we can still compute this quantity So now the original quantity minus the integral up to the cutoff. And this is a positive quantity due to the optical theorem. So this means that this actually gives a stronger bound than the previous one. Well, actually, this bound is interesting because now this Bn contains lambda through here. And at the low energy, some EFT may satisfy positivity. But if we naively increase the energy lambda, then at some point, we may find some violation of the positivity because we now subtracted some positive quantities here. So if this is too big, then we may find some negative one in this Bn. So this means that EFT is not valid there. So this states that this improved positivity actually gives a constraint on the cutoff of the EFT. So if we find some violation of this improved positivity, this simply states that the EFT is no longer valid at some scale. Then we get some constraint on lambda from using this improved positivity. So without knowing the UV theory, just using EFT, we can get a bound on the cutoff.
So when you say using EFT, do you mean like one loop?
One loop is of course okay. Well, in higher loop is also okay if the EFT is valid.
I see, but I suppose where you get problems with the EFT violating the bound, two loops is as important as one loop. Is that right?
This is also true, but I think this discussion is based on the validity of the perturbation theory. Two loops is important than one loop. But
right.
This is in fact different.
I was just wondering, is there ever a situation where you can reliably calculate in perturbation theory and yet see a unitarity bound violation from loop diagrams?
Yeah, if we find some exact calculation, if it's possible, then we can compute this imaginary part even at higher orders.
Right.
But still, this bound is applicable.
I understand, but in any practical situation, you calculate in perturbation theory, right?
Of course, yes, of course.
So basically, when perturbation theory is valid, this bound is not going to be violated, right?
I think so, yes.
Okay, thank you.
Yeah. But in some sense, this bound is stronger than this naive expectation. So even if the perturbation theory is valid, sometimes we find a violation of the positivity. So this means that the perturbation theory is okay, but the EFT should be violated. But anyways, this is a case of the, okay, do you have any question?
Right. I understand you can get a slight improvement to your bound.
Yes.
That slight improvement will be order G square, where G is a coupling.
Yeah.
Okay.
Because this is imaginary part.
And then once you've got the slight improvement, the order G to the 4 is probably negligible.
Mm.
So maybe you can get a slight improvement basically at one loop, practically speaking. Is that what you're saying?
Yeah.
Okay, thank you. Yes.
Right. Okay, now I go to the main part with positivity with gravity.
Sorry, if I might ask a question, continuing on Shiraz's question. So if I'm actually looking for an estimation of the new scale lambda, scale of new physics, then the one loop, I mean, so what's the idea that, so I can never be too sure of the value of lambda because my one loop calculation and two loop, all hard loop calculations will contribute more or less to this integral from that term. And as a result, I mean, it can only be an order of estimate. Order kind of estimate. I can never be sure. I mean, if there is a parametric separation between the one loop term and the two loop term and so on and so forth, then I could be more sure of the scale of new physics. But how can I be sure from this what the scale of new physics is if all the orders in G square are
okay,
and I'm only computing only the one loop, then I'm not doing the right thing, right?
Yeah, in the practical situation, we should use the perturbation theory, and we should use say one loop correction, and we may ignore two loop corrections. And then within this one loop, we find this inequality, and we can check whether boundary is violated or satisfied. And of course, if it's violated, one possibility is part of its expansion is wrong. So we have to think of the higher order corrections, and this may help the bound. This is one possibility. But in many situations, actually, we found that the violation of this improved positivity within the perturbation regime. So for example, essentially this M is a strong coupling scale. So if the energy is beyond this scale, then the perturbation theory doesn't make sense. But in many situations, actually, we can find the violation of this bound below this scale. This means that the perturbation theory is still okay.
So just to continue on that, there are two kinds of things one could try to constrain. That is the effective classical theory below a certain energy, and then one could also try to include loops.
Yes.
The classical theory seems very clean to me.
Right.
But once you start including loops, that seems less clean. Is this correct?
It's not necessarily less key. So yeah, because we have a higher order corrections, like more derivative terms, and we have these terms are suppressed by this scale, so M, in this example. So this M is a strong coupling scale. So I mean the EFT or part of its calculation is okay below this scale, even at the loop levels.
I see.
We need a counter term, infinite number of the counter terms because this is EFT. But below this scale, we have just a finite number of the higher derivative terms.
Yes,
you're saying that sorry, go ahead.
So you have a finite number of lower derivative terms. Now those lower derivative terms could get contributions, could be order g to the power 0, or g squared, or g to the 4, and so on. The parts that are g to the 0 are very easy to understand. The parts that are g squared and so on will start mixing with the loop diagram.
Yes.
Right. So that game of including the g corrections can only be done order by order in g, and
right.
very small corrections to the order g to the power 0 terms.
Right? Okay.
Which were the
Let's consider one example. Maybe this is easy. So for example, in the case of light by light scattering, photon scattering, actually leading one is a loop diagram. In that case, this is leading.
I see.
We don't have any tree level.
Okay, I understand. Thank you.
Thank you.
This is one example. Okay, any other questions?
So are you saying that the del phi to the fourth term doesn't acquire any contributions from higher loops? Just a one loop.
In the split of EFT, this coefficient includes all the corrections.
Yeah. So
this already includes.
In case you have a strong coupling,
yes.
You're essentially uncertain about what C1 is, right?
Yeah, in the strong coupling regime, yes.
Yeah,
but we are interested in the low energy, weakly coupled regime. Otherwise, we cannot do calculation. In that case, there is no ambiguity.
Okay, so in the weak coupling regime, it receives only contributions from the one loop and say 2 loops or something. That's what you're saying.
Yeah, we have an expansion, and at each order, we can do the computation without any subtleties.
Okay.
Yes. Okay, let's talk about gravitational positivity. I only have 10 minutes. But anyways, the difference is simple. So we have t-pole, and this is a problematic because we have a 1 over t. And as I said, we want to take a forward limit. So t goes to 0, but 1 over t means that we have infinity. In some sense, inequality is consistent because this diverges to minus infinity. So we get this inequality. V2 must be less than minus infinity. But of course, this doesn't make sense. But this quantity doesn't have any pole because pole is already subtracted. So this means that this quantity itself is finite even in the forward limit. So this is mathematical equality. So this is finite and this is infinity, means that we must have infinity from here. So this implies that we must have something like infinity minus infinity in the right-hand side. And if we can evaluate the remaining finite contribution after this infinity minus infinity, we may get some bound. So we have to do it in the case of gravitational positivity. And actually, this infinity is crucially related to the Lecce behavior. So let's consider this Lecce behavior. So imaginary part of the amplitude in the high energy limit takes this form. So power is now 2 plus alpha prime t. And if we consider t is negative, since we have 3 here, and power is slightly less than 2, this means that this integral converges. So if the t is negative, we have a finite value, actually. And if we take a t goes to 0, then we have a 1 over s here. Then the integral diverges. So the integral doesn't converge. So this means that this behavior is crucially related to this t-channel pole. And this is indeed the case in the string amplitude. So graviton t pole is related to the graviton SU Lecce state. So the idea is quite easy. So we just divide the integral into some intermediate scale to the high energy scale. So ms is some UV completion scale of gravity. And beyond which, so we assume that the graviton amplitude is lectured. So the graviton amplitude is given by this form. Then we now compute this term, because if the t is slightly negative, there is no any divergence, so we can do the computation. And in the finite negative t region, this integral gives this kind of expression. So originally we have a t pole from the graviton, and also we have a Lecce behavior in this integral, and this integral actually gives a 1 over t plus some finite contribution. And as a consistency, these two terms must be cancelled. Then what is main is a finite contribution. And since this is finite, we can safely take the forward limit after this cancellation. And actually, this finite term can be computed when the explicit form of the Lecce behavior is given. So if we know the UV property of the amplitude, we can compute this finite part. And this finite part takes this kind of form. So this is our ansatz on the Lecce behavior. So we put some function t here. And this finite term takes this kind of form. And let's define some scale m unknown to denote this scale. And one unsatisfactory point is that unfortunately, we don't have any way to determine this scale, size of this scale. And of course, if we know the UV complete amplitude, and if we can compute it, we can, of course, understand what is this scale. But we don't know UV theory. Then that's why we, unfortunately, at current stage, we cannot say anything about this scale. And there are at least two possibilities. One possibility is that this scale is related to some IR scale, like a mass of the light particles. And this possibility is discussed by essentially Imperial group, this paper. And this means that positivity is gravitational positivity is a this inequality. So amplitude is bigger than minus this quantity. But this is not so, this is interesting result, but unfortunately, this means that practically there is no positive constraint because gravitational amplitude must be proportional to Planck minus 2 here. And this is a possible lightest scale. So this means that this quantity is possibly the largest value of the gravitational amplitude. So this means that, yes.
Sorry, just sorry for interrupting, but before understanding this finite negative contribution, can I understand this cancellation mechanism a little bit more detail? In particular, okay. There was an alpha prime. What happened to that? Near infinity, the Lecce behavior went as s to the power alpha prime, s to s squared, s to the power 2 plus alpha prime.
So I didn't prepare the slide, but okay. So yeah, this is just a computation of the integral, and yeah, alpha prime appears many places. And
no, I mean, if you go to here, for example, the last
yes.
last equation, the first term is what? The pole, right?
Yes, first term is pole.
And the second term is coming from the divergence of the integral, right?
Yeah, sorry, opposite. First term is from the integral and second is pole, but it's not important.
Okay, so the first term, how does it become the integral term, the divergence from the integral, how does it become the Planck square? 1 over m Planck square times t. There should be some alpha prime because there was an alpha prime there, right? S to the power 2 plus alpha prime t.
Okay. So I didn't prepare the explicit result, so please check this paper. But anyways, yeah, originally we don't have any Planck because our answer is this one, so there is no Planck here.
Okay.
And this coefficient is computed by f and alpha prime, for instance. So we have some coefficient from this ansatz. And this must be cancelled because the final result must be finite. Then we determine this coefficient. This must be Planck.
Sorry, up to a number, it has to be this, right? Because the whole amplitude is classical string theory, so it's 1 over g squared. And then dimensional analysis will tell you that the right powers of alpha prime will come.
Right. So the g square, the fact that there is a g square would make it m Planck square.
That's right.
Up to a number, and the number presumably is precisely 1.
Yeah, I think the test is the number. Yeah.
So Katsuki, you agree, right? That number is important. That exact number is also important.
Yeah, exact number is also important. Yes, yes. Because if the exact number is slightly different, then we don't have any cancellation, and we have inconsistency.
Yeah. So I just wanted to see that in a fine detail. I will look at your paper for that more.
Yeah.
Detail. Thank you.
Sorry, I didn't prepare the detail, so please.
That's fine.
So okay. Anyway, so this is a case, but the more interesting case would be that this unknown is a UV scale, and in that case, this quantity is relatively small, and we find a non-trivial positivity bound. And actually, in that case, if we assume that this last case, so this unknown is done in the UV scale, then we get the so-called weak gravity conjecture type constraint on the gravitational EFT.
So the M unknown was what? The
M unknown is determined by this one, and this is our ansatz, its behavior, and this is overall the function of t, and this is t derivative of f essentially.
So is it essentially the place after which the behavior becomes s to the power 2 plus alpha prime t?
Right. Okay. So our naive expectation is this one, UV scale, because this is UV amplitude.
Right.
So we may,
in string theory, it's for t much larger than string scale, I suppose. Right?
Yeah, that's why they discussed that this would be IR scale. But here the t must be less, t must be 0. That's why it's possible to have an IR scale. But still, this is a UV amplitude, or Ledge limit. The Ledge limit is like a mixing between UV and IR. So that's why it's so difficult to conclude the size of this unknown.
Okay, thank you.
Yeah, thank you. So so if you want to, if you find the value of this unknown, it's very nice. But what we can do now is just assume the size of this unknown and get some phenomenological constraint. And okay, I don't have time, so let's skip the
Katsuki, we are flexible with time, so you don't have to worry about that. Yeah.
Oh, really? Thank you. So okay, can I have 10 minutes?
Yes, sure. No problem
at all. Thanks.
You can easily have half an hour more.
Really?
Yeah.
Thanks.
So Katsuki, just one general kind of reference set question. The fact that the graviton pole is cancelled by the Regge behavior, at t, the t equal to 0, part of the Regge behavior. Has this observation been made before? Yes,
it's already known. In the string context.
So where is it known? If you could tell me that would be pretty useful.
Actually, this is so well known. That's why I don't know who first point out this duality.
I see. Just
for example, if you consider type 2D string, the type 2 string amplitude, we have a gamma functions.
Right.
And then we can directly confirm this cancellation. So in the case of the type 2 three-level amplitude, this integral is essentially the infinite sum of the poles of the higher spin states. And actually, this sum, infinite sum, is exactly the same as the t-pole in the string amplitude. Yeah.
Sorry, just following up on that, Katsuki, just 1 minute. This is something Abhijit and I have discussed before. Suppose we were doing the heterotic string. Now the graviton exchange, and we were scattering not scalars but gravitons, just for instance. Then the graviton exchange would include contributions from Gauss-Born atoms. And at least naively would have a t-channel pole that scales not like s square, would have a contribution to the t-channel pole that would scale not like s square but some higher power of s. And we've wondered how that now s square fits very well with your Regge growth, because you'd have to divide by s cube, and that makes it sort of barely convergent, right? Because the Regge growth was s squared, there was 1 over s cube, and you're on the edge of convergence, and so you get a divergence in t. But we were wondering whether you could take this further, account for corrections to the graviton pole.
On a related note, there would be higher order contributions from even higher spin particles if you're considering string theory, right? So they would also contribute to s to the some higher powers, as Shiraz is saying.
Okay. To be honest, I'm not so familiar with the heterotic string, but one point is first, this pole arises from the low energy degree of freedom, because this is origin of this T pole is here. No, not here. So sorry. T pole is from the low energy part. So this is not the UV pole, because the UV particle pole of the UV particle must be resonance pole, not the pole in the first Riemann seed.
So that right. Even I was just talking about the IR contribution. The IR contribution, the T-pole would have some corrections, right?
But sorry, I have no clear explanation now, but I think that this residue of the pole is exactly 2, even in the presence of the higher derivative corrections. So this Gauss-Bonnet would provide another finite contribution, but not the residue of the pole.
I don't think so, because you say you could have 3 graviton. Gauss-Bonnet includes graviton coupling.
In the
it's a 3-point function from graviton.
Exchange diagram coming from one of the vertex being, let's say, Gauss-Bonnet or even higher, and the other vertex, for example, let's say just Einstein gravity vertex, and then you would have scaling which would be higher in s, higher power in s divided by t.
Okay. If the external particle has a spin, then we may have other contribution.
Yeah, let's say the external particles are gravitons.
Graviton.
Yeah, in that case, but I think the situation is the same.
Wouldn't they be suppressed by orders of the Newton's constant?
Yeah, of course, but
it would be suppressed by M string.
Yeah,
this
yeah.
is part of the classical effect. The question was, Katsuki, that your mechanism was such a robust one that you had the S square and then small correction scaling for Regge growth. That seemed to be tied with an S square behavior.
Yes, yes.
But it seemed like there could be corrections to this. This was the question Abhijit was asking.
But I think there is no correction to the residue. Yeah, there are correction to the finite part, but there is no correction because I think that this power is completely determined by the angular momentum conservation.
Well, if you have if you have graviton scattering, 4 graviton scattering, and you have Gauss-Bonnet terms, then there will be a contribution, right? You can calculate.
Yeah, there is a contribution from the Gauss-Bonnet.
There's a contribution.
So Katsuki, what you are saying is true. If the external particles are scalars, then the spin determines the power of S.
Yeah.
But when the external particles are gravitons, as they can easily be.
Yeah, there is some contribution from the polarization state.
Yes.
Yeah.
So something times the S squared.
No. Oh, something times S squared.
I think.
No. We calculated this in a paper. It's not S squared.
Oh, really?
Yes.
Like S cube for some.
We got S cube with Gauss-Bonnet and Einstein, and then we got S to the 4 with 2 Gauss-Bonnets.
When 2 Gauss-Bonnet are there, then there is S to the 4. Yeah, S to the 4 by 3.
Of force?
Yeah.
Even the. Yeah. Oh, really? Well, I don't know it. I didn't know it.
Okay. Thank you.
Really? Thank you.
Yeah. Thank you. Thank you for question.
Sorry, I have a slightly vague question. So, here in the language of dispersion, since you had some bad behavior in the IR in form of this T-channel pole, and you sort of accounted for it by a bad behavior in the UV in terms of this Regge growth. Okay, not bad behavior, but you isolated that piece which would compensate this bad behavior in the IR. Now this behavior in another way to look at these IR UV consistency conditions is causality conditions. And in the paper by Maldacen, Edelstein and others, they showed that higher derivative corrections to gravity. I mean, it's a similar kind of Regge behavior that like cures of causality. Is there a clean way to see the relation? Because that's a constraint on the graviton 3-point coupling. Here, this Regge behavior seems to cure the T-channel pole in the IR. Is there a clear way to connect these two observations? Because it seems this, like the same thing cures both of them, and they're both higher UV consistency conditions.
To be honest, I think that there are some relations, but I'm not sure whether the argument is quite regular. Yeah, even in this argument, we naively expect the Regge behavior is only the way to solve this inconsistency, but mathematical proof is different.
I see.
Yeah, so one comment about that. Katsuki is getting a condition even when the low energy behavior is just Einstein. Whereas EMZ would get no condition in that case. Even if it's pure Einstein, he's finding the necessity for some.
Right.
So, okay. Okay, so let's move to the implication of our bound. So again, I summarized our assumptions. So these 4 well-accepted properties plus additional assumption is a single scaling. So we assume that the F is scaled like a scaling or dimension full parameter of this F is determined by UV scale. And in that case, our statement is that this quantity has to be greater than this small quantity. So small violation of the positivity is allowed, but this should be suppressed by Planck and UV scale. And just one example, let's consider some renormalizable QFT coupled to GR. So this is a non-gravitational part, and this is a gravitational amplitude. So that they have a different scaling in terms of Planck. So this non-gravitational part is scaled as a Planck is independent of Planck, and this GR is scaled as a Planck -2. For instance, if you consider light-by-light scattering, so this is a non-gravitational contribution from the electron loop. And this GR contribution contains a 3-level graviton exchange. So this proportional to Planck -2. And also we have this kind of one loop diagram. So this is one loop, but the one loop in the matter sector, not the graviton sector, because loop of the graviton is suppressed by Planck. So it gives a Planck -4. So as the Planck leading order in Planck, we have this kind of loop diagrams. And we can define the B after subtracting some integrals and also poles. So we subtract the pole. So this 3-level graviton exchange doesn't contribute to the gravitational part of this B. So the leading correction in B is actually one loop diagram. So in this example, this is computed by this diagram, and this is computed by this diagram. And the statement of positivity is the sum is positive, almost positive. And the interesting point is that this gravitational contribution actually provides a negative contribution in at least known processes, all the known processes. So this means that the sum is positive, but this is negative. This implies that this inequality. So roughly speaking, this may say that the non-gravitational amplitude has to be greater than gravitational amplitude. So this is similar to the so-called weak gravity conjecture. So gravitational contribution has to be weaker than the non-gravitational ones. Of course, you may say that this is trivial because this is Planck suppress, so this amplitude must be less than non-gravitational amplitude. But actually, this inequality is not trivial because of lambda, because we can increase the lambda to explore the EFT to a higher scale, and then we may find some inconsistency as some finite lambda. So let's see this behavior for details. So we assume that the QFT alone, so renormalized of QFT, is UV complete when the gravity is decoupled. So this means that we can compute the amplitude by using this renormalized of QFT even at the UV scale. So this means that this dispersion relation is trivially satisfied in the renormalized of QFT. But in that case, the point is that the lambda appears here. And if we take a lambda goes to infinity, we have infinity, infinity. So this is 0. So this concludes that the BQFT, so non-gravitational contribution, has to vanish when the lambda is infinity. And of course, it's positive for finite lambda. And these are the explicit calculations in the case of light-by-light scattering. So if we consider spin half loop, we have a lambda -4. So it decays as lambda, and it goes to 0. And also in the case of spin 1 loop, in the case of electroweak sector, we have a charged spin 1 particle. And this kind of diagrams provides a lambda -2. So again, this is decaying. So we have a 0. And if you have a charged spin 0, again, the same. So we have lambda -4. So all the cases are consistent with the general argument. So BQFT must be 0 when the lambda is infinity. And in this case, you see that this spin 1 gives a dominant contribution at high energy, high lambda, because the decaying law are different. So at the UV, if the lambda is sufficiently large, we can only pick up this weak contribution, spin 1 contribution. So let's pick up this one. On the other hand, gravitational interactions are not UV complete. Of course,
I have a question.
Yes.
So when you are considering the range from lambda square to infinity, don't you have to consider the fact that there could be poles due to particles which have masses in that range? For instance, say stringy higher excitations.
Okay, first I should say that the lambda is less than string scale because this is our derivation, and already we have split its integral to the less than string scale and above. So this means that the lambda has to be less than this scale.
Okay, so, but when you're considering from lambda to infinity, okay.
This is when the gravity is decoupled, then we may take a lambda goes to infinity. But the point is that we just want to confirm this behavior. So B decreases as the lambda decreases. So lambda is a function of the inverse of lambda.
Sorry?
And these behaviors are determined by this dispersion relation, or easily inferred from the dispersion relation. So B decreases as the lambda increases, sorry.
All I'm saying is, shouldn't you consider the effect of the poles between for higher spin particles which are string excitations? Why shouldn't you in this range?
Okay, I think we should separately discuss two cases.
Okay.
This is just a non-gravitational part. That's why we can formally take lambda goes to infinity.
Sorry, and lambda in this case would be the mass of the W boson?
No, lambda is exploration scale of the EFT.
Right.
So assume the lambda EFT is buried below lambda.
Right, but for the EFT that you're calculating here, what is running in the loop?
Here, I only take into account the leading collections, so we don't talk about the running here.
Yeah, right.
But in principle, we can include it.
Yeah. So, sorry if I understand, Katsu, you're saying, suppose it's the standard model, Shiraz, up to the scale lambda. You know?
Yes.
But I was thinking we could just do QED. Couldn't we just do QED and then W bosons are like a cutoff for QED or not?
Yeah, in the standard model, we have to take into account all the collections. And I just pick up the QED collections, QED contribution, weak contribution, and spin zero contribution. But of course, the result must be the sum of all the contributions.
Okay. Okay. So lambda is the scale at which standard model breaks down, you say?
Right, right.
Okay. Okay. And just let me understand this, if you don't mind. So you say that there may be contributions from new physics at scales above which the standard model breaks down.
Yes, yes. And
okay.
This new particle may contribute. But the interesting point is that the mass must appear in the denominator.
Yeah.
So this is easy to understand.
The interesting point is that
this mass appears in the denominator here. So
right.
Okay, let's explain. So this is dimension -4.
Yeah.
So we know that this must be proportional to lambda -2.
Right.
And we need to put some dimension here. But all the gamma are massless. So only the possible mass parameter is the mass of the internal state.
Right.
So this means that, okay, you can put the new spin-1 particle at high energy, but it appears in the denominator. So that this contribution is subleading compared with the weak boson contribution.
I see. Now, is this lambda here a precise number? I mean, can you use these things to bound lambda with numbers, or is it some order of magnitude kind of thing?
We can give a precise constraint.
Now, what does it mean, scale of new physics, in some precise way?
Yeah, so, okay. Okay, first, I should say that the GR contribution provides a negative contribution. So this means that if we increase the lambda, at some point, we have some violation of the positivity. So this means that this QFT or standard model coupled GR must be violated at that scale.
No,
this is one conclusion.
Suppose new physics was a new particle, for instance.
But just new particle doesn't help this bound.
Right. So no, I'm just trying to understand what the definition of lambda is. If there's a precise definition, or it's ambiguous up to like order one numbers. So suppose there was a new particle, and it had a mass. You might think that mass would be the scale of new physics, but the new particle will presumably be unstable, so the mass is not a precise number. So I can't understand what the definition of scale of new physics is if you want to make it precise. Of course, if you want to say up to order one numbers, then I understand. But if you say that it's 1 TeV is different from 1.2 TeV, then I don't understand.
Is it some non-analyticity in the S matrix, or
there are already non-analyticities in the S matrix, right?
Yeah. So that's, I don't know.
So okay. So could you wait for a while? Maybe I should explain the result first.
Okay, sure.
We must wait, and I know the least, but Katsui, let me suggest an answer which everyone will find unsatisfactory, which is, if you evaluate loops in a precise renormalization group scheme, then Katsui will give you a precise cutoff in that scheme. And then that's not a very physical answer, but it's a very precise answer. Okay, sorry. Okay, go ahead. Ignore my comment. Sorry.
Okay, anyways, we can compute these amplitude by using perturbation theories. And this is weak contribution, and this is GR contribution. And GR gives a negative, so we have some violation at some point. And this is actually the result.
Okay, yeah. I'm very, very sorry. You're showing this, but roughly up to factors of alpha, it is lambda must be smaller than MEM Planck, right? There's an MW also. Sorry.
Yeah, yes.
I mean, what's interesting is there's an ME there, right? It makes it quite low.
That's right. So, but in the standard model, we have QCD. That's why the QCD scale is less than electroweak scale. So as I said, the mass appears in the denominator. So QCD is a dominant. So first, I should say that in the standard model, QCD determines the cutoff finally. And we can compute the precise number here. And this is a cutoff. So this 10 to 16 GeV is a cutoff of the standard model coupled to GR. And as I said, even if we put the new particles, heavy particles than the standard model particles, the mass appears in the denominator. So meaning that it is subleading. So the precise number may be defined, but at least it may not change the value drastically.
But wait, what does I didn't understand this. What does QCD have to do with it? You mean loops including QCD? I didn't understand that comment at all. Sorry, just elaborate on that.
Okay, so roughly speaking, of course the QCD is non-perturbative, so result is slightly different.
I see.
Roughly QCD gives a similar form.
How do you know that? How do you know that, Katsuki, if you allow that to run in the loops?
This is a model to compare the QCD process. So of course, QCD is non-perturbative. We have many diagrams, and this is a kind of phenomenological model. So assume that the photon is transformed to some vector mesons, and these vector mesons interact with under the hadronic interactions. And this is called Pomeran exchanges, Lecture exchanges. And unfortunately, we cannot compute this diagram, this behavior by using QCD itself, QCD itself. But we can determine these coupling constant or behaviors of these Pomeran or lections by using experiment. So this is a kind of phenomenological model, and that we know the values. Then we can compute this process.
I see, but the scaling with lambda, I mean, if lambda is sufficiently high, given asymptotic freedom, you should be able to obtain that scaling.
But the point is we are interested in Lecce limit. So T is small. So T is still less than QCD scale.
I see. Okay.
That's why the usual asymptotic freedom cannot be.
Okay, you're right. Okay, sorry. Okay, I understand. Thank you.
Thank you. But anyway, we can compute the QCD process, and we can get this result, and we get some cutoff.
Could you say again what this gravitational contribution was, please, where it came from?
Sorry.
This
BGR2. There's some noise, so sorry.
Sorry, BGR2, the gravitational.
BGR is this guy. Contribution from this loop.
And how did you get this, please, again, please?
Just computing this diagram, but we can understand the behavior of this guy. So this
it's a tree-level exchange with a graviton, some loop, and then a tree-level graviton.
This is loop level.
Loop level, but the graviton is at tree level.
Yeah, graviton is tree level.
I see.
Only the matter loop.
I see. So I see. Thank you. So you say this you can reliably compute, and that plays into your bound. Okay, thank you.
Right.
So I see. So sorry, Katsui, this is a very interesting scale, of course. Are you saying ME, M Planck, MW, and factors of alpha conspire to give you 10 to the 16 GeV?
Yes.
That's very interesting.
This is in some sense universal.
Sorry?
This is universal, right?
Yeah.
Even if you put the new particle, this doesn't change.
I see.
As long as this new particle is heavier than QCD.
And so you get the gut scale out.
Yeah, somehow, yes. It's surprising.
It's a remarkable conspiracy. I've never seen this numerology before. Okay, that's very interesting.
Yeah, at least for me, this is super surprising. Somehow we find the gut scale by using this consistency.
That's amazing.
So I didn't understand how you got that there was an inconsistency about this. What goes wrong about this scale?
So if we use a standard model coupled to GR beyond this scale, we find a negative B. And negative B means that unitarity, of course, this is a stability, but accepts these assumptions, this quantity has to be greater than this one. If we find some violation, this means that at least one of these assumptions must be violated.
Sorry. So the gravitational amplitude gave you some negative term, and that was
right. That's the reason.
That's the reason. And you say that you can calculate everything else reliably within the standard model, and it's not positive enough.
That's right.
Okay. Thank you.
Yeah, perturbation theory are still okay, but we find some negative.
Right. And gravity is weakly coupled at the scale. I mean, the loop
right.
is not important.
Right. because this is still less than Planck.
Yeah.
So sorry, Katsuki, just one last thing, Katsuki. One last thing, which is how important was that QCD part in this numerology, in getting the scale? Was it important that you had to put in the lambda to the 1 point, this stuff?
It's slightly important. Yeah, in our paper, we slightly discussed some other possibilities of this QCD amplitude, but it just changed the 1 order of magnitude. 10 to 15 or 10 to 17.
I see.
But it's almost like this.
Okay.
Are you assuming a desert between the electroweak scale and the higher Planck scale or whatever higher scale you have?
Sorry?
Are you assuming a desert between the electroweak scale and the...
No, I didn't assume anything. Just use the standard model on GL and this positivity.
Yeah, but there could be other particles also. We don't know, right?
Yeah, but even if you have some new particles, this doesn't contribute because this is a reason. So if we have a new particle, we get a similar conservation like this. We have a new loops here, but mass appears in the denominator, and mass is greater than QCD scale. This means that this value, a new contribution of this one, is smaller than QCD.
I see. And just to completely understand, so you're computing the 4-photon effective coupling. Is this
yes,
F to the 4 term? Effectively, some F to the 4 term in the Lagrangian? Field strength to the 4th?
No, you just use the standard model on GR.
I understand, but if you wanted to isolate the coefficient of this in an effective field theory, this would be the trace of
yes.
F
in
to
that
the
sense, this new particle gives a F to 4 contribution.
Yes, I see. And you say that this you can prove that this coefficient has to be positive because by doing just like the delta.
Yes.
Delta to the 4 was positive. In the same way, this is positive, but you get a negative contribution from gravity, and therefore there's potential tension when you go to high enough scale.
Right.
Okay, thank you.
Yeah, gravity is always important.
So Katsuki, let me just say it and you tell me what you have proved is, as long as this QCD part, which, I am not so sure, but okay, what you're saying is as long as that QCD part is correct, given the standard model, regardless of what other particles might be present, you can show that there has to be there has to be fundamental new physics appearing at the gut scale.
Yes.
Well, that's an amazing thing. Just from very reasonable assumptions.
Yeah. At least under our assumptions, we can show it.
But your assumptions are okay. Yeah, you all understand that this seems so reasonable. Wow.
Yeah, I think so.
Yeah.
Thank you.
I'm really sorry, but what you answered Shomdatta, but I didn't understand. If there were new particles in the middle, why couldn't that save the day?
Sorry? Say again.
If there was some new physics in between, that could change it, right, or not?
Yeah. It's like the MW Shiraz. Sorry, Katsuki. He's saying it's subdominant if that particle has mass bigger than MW. Right, Katsuki?
That's right. Completely. Exactly.
So you're saying no new degrees of freedom could change this.
Right, as long as it's heavy.
I see. Yeah. But actually, sorry, while Shiraz, I'm very sorry. Suppose there was a new suppose for a minute we didn't know that there was the Higgs boson and there had been Technicolor, a new strongly coupled sector. This lambda to the, I don't understand this lambda to the QCD part. If there had been a new strongly coupled sector just above the TeV scale or wherever, would that have changed things? Or are we certain that it would move between 10 to the 17 and 10 to the 15? So suppose there was a new strongly coupled sector with the strong coupling scale, not 100 MeV, but let's say 10 TeV. How much would this have changed?
I think it doesn't change because, first, this behavior, this power is related to the growth, energy growth of the cross section. And this is related to the constant cross section. The constant cross section b to -2. And we know the Floissart bound. So even if the cell is strongly coupled, the growth of the cross section is up to logarithmic of energy. So it's slightly higher, faster than constant cross section, but it's almost the same because this is log. So this
And
means
what about
that, yes,
sorry,
sorry.
what about the contributions to the loop diagrams that you have on the right, where you have a particle running in the loop and a graviton coupling to the loop? What about those contributions? If you have higher mass particles, do they change the picture in any way?
To be honest, I'm not sure, but I think
what is the mass contribution coming from that loop depending on the mass of the higher mass particle? How does the mass figure? Does it still come in?
I think you're asking about the running, right?
I'm asking about this electron loop running in the electron running in this loop with the graviton coupling in the previous slide, with the graviton coupling to it. So if you instead of the electron you have a certain higher mass particle which is beyond the standard model, then what are the contributions coming from that?
I think the same, because this is dimension -4, and we have a Planck -2 here. So again, the mass should appear here.
Yeah, that's right. If you integrate out the electron loop, you'll generate a effective graviton, and there's dimensional analysis will probably put the ME in the denominator.
Yeah, this is just dimensional analysis, but it concludes that the heavy particle should be subleading.
Okay.
Yeah, so that's why I think this is quite interesting. And still, in addition, there are also another interesting things by doing some kind of swampland sort experiment. So this is a completely different topic, but let's do some sort experiment. So let's consider what if there is no weak and QCD scale. So of course we know, but let's consider there is no weak and QCD sector. In that case, the cutoff is determined by disk inequality. So this is again interesting because somehow the massless fermion is swampland. Because if the ME is 0, then the lambda must be less than 0. So this doesn't make sense. On the other hand, we know that the Higgs mechanism, so mass of the fermion is determined by Higgs pair. And in the electroweak sector, actually this is determined by ratio between the two masses, and both are proportional to wave. So that's why this in the electroweak sector, massless limit is somehow consistent. This is also, I think, interesting. So somehow in our nature, we have a Higgs mechanism, and this Higgs mechanism is preferred from this kind of consideration.
I have another question. Can you go back to the previous slide, please?
Okay. This one?
The previous slide.
This one?
No, the previous.
Maybe this. Or
yeah.
This?
So here, this one. Yeah, this one will do. Here, the graviton coupling is associated with G Newton, right? I mean, G Newton figures.
Yes.
So it's suppressed hugely compared to the other terms.
Right.
So why are you saying that they are comparable in the sense that they kind of affect each other? Maybe
this figure is better. So in the low energy, low lambda, of course, others are dominant. You see, it's almost difference is 10 to minus 30. But these are the decreasing function in lambda. So at high lambda, some point we have a violation. Well, at some point two are comparable and we have violation.
But if you're inching closer to higher and higher lambda, then higher stringy modes will come in, don't they?
No, lambda is still less than the string scale.
You're still less than the string scale.
Yes.
But the point at which gravity becomes strong, there I would presume that stringy modes will start appearing, right?
Yes. So for instance, if the actual string scale is a 10 to 15, then there is no inconsistency. Because this discussion says that the lambda should be less than this value. And the lambda is again less than string scale. So that if the string scale is greater than this value, then there is inconsistency. But if the string scale is less than this value, then there is no inconsistency.
No, what I'm saying is G Newton will start mattering when the when gravity becomes strong, right? And unless G Newton mattering, you don't have to consider their effects. And once G Newton becomes strong, you have the stringy modes coming in. That's all I'm saying.
Not sure, because still this scale is still less than Planck. So gravity is still weakly coupled.
As long as gravity is weakly coupled, those terms wouldn't matter.
Yeah, at least. This is a kind of bottom-up approach. So at least the energy is less than Planck. We don't have any self-inconsistency.
Okay.
Does it answer your question?
Say that again. I didn't get you. What did you say?
Does it answer your question?
No. What did you say? What was your answer?
I say that as long as the lambda is less than Planck, then there is no self-inconsistency in the calculation.
No, I mean, lambda is less than m Planck, you're saying?
Yeah. Yes.
Yeah, but as long as lambda is less than m Planck, the gravitons are weakly coupled. That's what.
Yes.
Yeah, and then the terms wouldn't matter. They wouldn't cancel in anything.
Right.
Because they would not be comparable to the other terms. So once they start mattering, you have to consider the stringy modes as well.
Yeah. So if we have some violation, this implies that we have to consider the stringy mode. Yes.
Sorry, was the tree level exchange due to the two photons to two photons by tree level graviton exchange, that also contributed to this F to the 4 term?
Sorry, say again. I missed some question.
Photon going to graviton, going to photon, that also contributed?
Photon, you mean the external one is graviton or photon?
Then tree level exchange with graviton.
This one.
Yes, that also contributed?
That also contributed, but this is a pole subtracted amplitude. Okay. That's why in B, they don't appear. It doesn't appear.
Okay. And I see. Okay, thank you.
Thank you.
Katsuki, we must let you go on, but and I'm sorry, I'm so ignorant about all of this stuff. But just to get rid of the QCD uncertainties, can't you run your argument at T bigger than the QCD scale? Does it have to be that you get all this only when T goes to 0? Sorry, I apologize for a dumb question.
Sorry, please let me know your question.
Do you have to take the T going to 0 limit? Can you get something interesting for a value of T which is above the QCD scale, say, or if you allow it to float?
Sorry, I don't understand your question.
So no, never mind. Go ahead. I'll ask.
Sorry,
it's probably a stupid question. Go ahead.
Sorry. Here we want to take a further limit, so T is less than QCD scale. Otherwise, we cannot use for optical theorem. And okay, anyway.
Okay.
But
say once what you just said. You wanted to take T less than the QCD scale. Otherwise, we cannot use optical theorem. Optical theorem. Okay. Positivity of that object is not guaranteed.
Right. Okay, maybe I can summarize my talk. So I can stop here, I think. Yes, thank you very much. Thank you for many questions. I really enjoyed.
Let's thank Katsuki for a very nice talk. Other questions? Yeah.
Yeah. Katsuki, it's a really interesting and very beautiful talk, and thank you very much. But there's something I'm finding very non-intuitive. I'm finding it extremely non-intuitive that you're getting a violation of unitarity when within effective field theory, when effective field theory is weakly coupled.
Yes.
I would have thought you just unitarity is Kutkowski's rules. And Kutkowski are manifestly obeyed in effective field theory, in a weakly coupled theory. So how is it possible that you take into account only weak coupling effects in perturbation theory and end up with a violation of unitarity?
I think this is not necessarily to be the violation of unitarity. It may be a violation of the other principles, probably.
Which principle do you think is being violated?
It's a difficult question because all the assumptions are related, but I think it's crucially related to the causality, I guess.
Causality, but you mean that just technically, are you saying that there would be a new non-analyticity?
Because yes, because
even that we can check, right? Because all the processes we can compute in Feynman diagrams, and either there is a new non-analyticity or there isn't. So it's just all under control, right? It's weak coupling calculations. How can that violate anything?
Okay, for example, the simple example. So in this example, this scalar example, the sign of C1 is related to the sound speed of the scalar wave around some non-trivial background. So we can consider some time-dependent phi background, say phi is t.
Yes.
And we can consider perturbation around this background, and we can get the sound speed of the perturbation.
Yes.
And this sound speed is related to this C1,
right.
and positive C1 is related to the subluminal sound speed, and negative C1 lead to the superluminal sound speed.
Correct. I agree with this. But suppose you calculated the C1 in some effective weak coupled situation, you will always find an answer within the validity of that effective weak coupling that is positive, right? Within that weak coupling expansion, you'll never find a negative answer. So in the same way, what you are doing here is doing some effective weak coupling calculation and finding something violated. And I find that somehow very non-intuitive.
So, yeah.
Can I ask something related, although it might be not, and then I apologize, which is, okay, let's throw away the gravity diagrams and then keep just the standard model diagrams in light to light scattering. Now, you showed that if you just kept those diagrams and let lambda float to infinity, what was your bound into zero? Their contribution into zero, right? All of them scale like lambda to some negative power.
Sorry, the internet was unstable, so
okay. Let's throw away the gravity contributions to a light by light scattering. Only keep the standard model contribution.
Right. Okay.
Then if I let lambda, the cutoff, go to infinity, all these B2, QED, weak, etc., everything went to zero.
Right, right.
Would that be an inconsistency by itself?
No. There's
no, right.
Always this is positive.
So because it's at least maybe the bound is greater than equal to zero, let's say. You know, whatever.
Then we found some inconsistency because this approach to zero.
Right. I'm just saying if the standard model was the full theory of the world, there was then lambda would be infinity, right?
Right.
Then you would not have any violation of your four principles. Is that correct?
Oh, right, correct.
Okay, so if I understand, you are getting an upper limit on lambda after you include gravity, and you require that the full system then meets some positivity condition.
Exactly.
So
how can this happen? How can this happen when it's all computed in perturbation theory? Because I can just examine all my perturbative graphs and they will obey all my principles.
I think it's a little bit more than Katkowski's rule somehow, because there is some UV contribution that is demanded to be positive.
Yes.
And then you have the infrared contribution, which is being computed perturbatively.
But the UV contribution is completely I mean, we're not, since the UV contribution by itself is positive, it must be that the infrared contribution is giving you a negative number. Otherwise, there could be no violation. Right? Because the part that you can control has to be...
So you compute all the infrared contributions and demand them to be appropriate sign.
Good, right. So how could it, if all those calculations are within perturbation theory, how could they not be the appropriate sign?
Well, the gravity was negative, right?
Even gravity is negative in perturbation theory. And gravity obeys all the rules, Kutkowski's rules and so on, within perturbation. I'm sorry it's a vague question, but it just feels non-intuitive to me that something like this could happen. It's probably stupid. I'm sorry.
I think that it's like similar to the, but it's still perturbation. Yeah, idea itself is same as predicts a weak Higgs boson from the weak sector. So if you just use the theory of the weak boson as the energy above the Higgs scale, then you find the inconsistency. So this is same in some sense.
Okay, but wouldn't it be that in that calculation, at some point, the diagrams that would have violated unitarity would also have become non-perturbative in the sense that one loop would have become, two loop would have become as important as one loop?
But still, it's perturbation regime. Two loops can be less than one loop.
I see. So you're saying that within perturbation theory, it's possible to violate Kutkowski's rules?
It's not necessarily that this rule, but this positivity can be violated.
But doesn't positivity follow from Kutkowski's rules?
Yes.
So then you're saying you can violate Kutkowski's rules in perturbation theory?
In a sense, maybe yes.
How can that possibly be? Because perturbation theory obeys. I'm sorry for the stupidity of the question. But just this seems to be the main part.
Yeah.
You can reliably compute and find this violation sounds unintuitive.
Okay, how can I explain?
So sorry, just for the uninitiated, Shiraz, your point is gravity by itself in perturbation theory should not lead to violations.
So your internet is not very clear, Sandeep, but if you're asking whether gravity introduces a violation, I think in perturbation theory it does not.
Okay.
Yeah.
Then I don't know what's going on.
So in particular, Katsuki, if you just do this swampland criteria for pure gravity, would you find some inconsistency because there is nothing to save you?
This way?
Yeah, I mean, let's say here you have these various possibilities, right? If we know weak and QCD sector, etc., and massless fermions maybe in swampland, etc. I was wondering, if the gravitational contribution is negative, then would you say something about pure gravity being in swampland or something like this?
In pure gravity case?
Yeah, in pure gravity case, or I guess you don't have that diagram with the photons running, with the electrons running.
Yeah, pure gravity is subtle because subtlety is proportional to Planck -2 and some scale. But I think in the pure gravity case, this amplitude itself could be Planck -4.
Okay.
But I think it's also interesting. This is also related to the UV property of the amplitude. And for the previous question, I think at least from the mathematical level, the inconsistency arises because this is too big, in a sense. So this quantity minus this imaginary part has to be greater than 0. This is a consequent prediction of the positivity. And if we naively use the EFT beyond its original cutoff, then the imaginary part may be bigger than the original UV complete amplitude. That's why this gives a negative value.
Okay.
So at least mathematical level, this is answer, but it's not intuitive.
Thank you. It's probably a very stupid question. I'll look at you.
No, thank you.
It's late, but ask you, there's tons of other things you could think of besides light by light scattering.
We are now discussing other scatterings.
Oh, I might have, yeah. I mean, if you get, go ahead, please.
sorry. In that case, we can get other bound on the coupling constant. For instance, in the electroweak sector from the right by right, we get this kind of bound. So Yukawa coupling is times the Weinberg envelope is bigger than this value.
Yeah.
But from other scatterings, we may get say the G1. So gauge coupling has to be bigger than this kind of value, or other gauge coupling has to be bigger than this value.
Well,
so
if you get the gut scale out through a number of ways, then it gets really even more exciting. It's already tremendously exciting. Two different kinds of some new numerology again lands you on the gut scale. I mean, then you're like, this is a sign from God. I see.
Yeah.
Okay. Thank you. Thank you.
If there are no further questions, let's thank the speaker again.
Thank you very much.
Thank you.
That was a great talk. So thank you so much.
Yeah, thanks a lot. Wonderful.